Hi, in this video we are going to learn how to take an exponential equation or a model and rewrite it without the horizontal shifts or stretches that it might contain. So, what does that really mean? We are going to take something that looks like this and change it into something that looks like this. Notice that that -4 has disappeared and the number in front has changed. So let's talk about how we're going to do that. We have to know our exponent rules and how they work backwards and forwards to understand this process. So our first rule is when we are multiplying two values that have a common base and they have exponents. In that situation, we are going to add those exponents together. This is typically the direction of the rule that you're most used to seeing, maybe the only direction you're used to seeing. What we're going to need to do is go backwards with this rule. So just recognize that these two things are equal, right? If I start with something where the exponents are being added, I can break it up into a multiplication problem with the separate exponents here. All right, when we have division with common bases, that's going to result in the subtraction of the exponents. But like I said before, this rule works both ways. So if we ever see this exponent with subtraction, we could either rewrite it as a fraction, or we could also treat this -y as just a negative value that's being added and still write it as a product. And you'll see how I do that later on. The last rule that we need to remember is when we take a base that's already being raised to an exponent and we raise that to another exponent. That's when we multiply those two exponents together. And just like the other two, this rule is working bidirectionally, right, in both directions. So if we see a product, we are able to split it up into an exponent with another exponent there. Okay, so let's put this into practice. Our job is to rewrite whatever these expressions are in the form a times b to the x. We're allowed to have a coefficient, we have a base, but in the exponent, we only want the variable, okay? So this variable, it happens to be a t, right? So just think of this as x being a t instead, which is fine. But this +1, that's gotta go. This is an issue. This isn't allowed to be in this format here. So we had our rule, when these were being added, that we could then split it up into a product. So let's do that. We now have a product of two numbers. They have the same base, right? They both have the 1.2. One of them got the t as the exponent, and the other one got the 1. Well, in this case, 1.2 to the 1 is just 1.2. And it's much nicer if we write that in front. That's our a value. Our b is the 1.2 inside the parentheses, and there is the exponent by itself. Let's see another one. 2 to the 3y. In this case, we have a 3 being multiplied with a y. So the product means that we can split it into an exponent being raised to the other exponent here, right? So notice I chose to put the 3 with the 2 because that's something I can simplify, right? I could have reversed the order of these, but that's not going to help me. This is something I can work with. So now if I raise that 2 to the third power, I get the 8. And now I have a 1 that's invisible, right, for my a value, a base of 8, and my exponent is just the variable y. Let's do one more. We have 7 times 1/3 to the x minus 3. The only issue here is the -3, right? We don't want that there. So we have some subtraction, and this is the one I was talking about, how it might be better if we see this as an x plus -3. Okay, so that we're using the same rule here where we split it into a product. So that's what I'm going to do. I split it into the product of a 1/3 to the x and a 1/3 to the -3. That gives me something to work with because this 1/3 to the -3, if you remember your exponent rules with negative exponents, means we're going to take the reciprocal of the 1/3, that's a 3, and take the negative exponent and turn it into a positive exponent. All right, so this 3 to the third, that simplifies to 27. That can now get multiplied with the 7 in front here. So now we have an a value of 189. Our base stayed the 1/3, and our exponent is just the variable of x. So you might not see why we're doing this yet. One reason is that it's simpler to look at, but it also is going to help us with our graphing in our next topic. But before we do that, you obviously want to do some practice. I wanted to show you one more example. We're going to switch over to Delta Math, just so you can see an example of what this is going to look like. And you're also going to notice that we're putting some of these rules together here. So we have a 3t plus 3 in our exponent. That is a product and a sum. So that's a little complicated now, right? I would like it if it was just a product or just a sum. So let's think about this. Could we write 3t plus 3 as a product? And we can. So 3t plus 3 could be factored. When we factor something, that means we're writing it as a product. I'm going to factor out a 3. But really what's happening here is that we have a multiplication problem. So let's take our base. So our base was 1.3. Our a value to begin with, right, is a 3,000. Let's write that down. So this is what we're really working with now. Okay, so this means that we now have the 3,000 in front, a 1.3 that gets cubed, and then that gets raised to the t plus 1. So let's see what we could do with this. 1.3 cubed, we can find what that value is. I got 2.197, and we still have that exponent of t plus 1. So this time, we have to use a different rule after we just used this product rule up here, and that's okay, just more work. The rules aren't changing though. So since this is a sum, this is where we split it up into a product of a base of 2.197, that gets a t, and another one, same base, gets an exponent of 1. Since these are just constants, they're going to get multiplied together. Wow, and they get multiplied to an integer. That's amazing. I got 6,591, and we have our same base and our t in the exponent. So that is what Delta Math is looking for. And the reason I know it was looking for that, I can see those spaces, right? It says right here, a times b to the t, and we have these spaces to type in. And we could do that, and we would get the answer right. Okay, so our last slide here, I've given you 3 things to consider, 3 expressions. I want you to think about if these expressions are equivalent or not equivalent to this expression up here. Okay, so take some time, work it out, use your rules, and when you're ready, you can unpause the video and see how you did. All right, so let's see how you did. Lots of things that you could do. You could try to make these match this. We could try to make this match this. We could make them both into something different, okay? I'm gonna do what's easiest for each one of them. So I'm just gonna go look and see if there's any simplifying that stands out. So on this first one here, I noticed that we have a 2 to the 4th, right? I know that that's 16, which would mean that we have a 16 to the t over a 16 to the 1. Well, that's good to know because we had a rule that says that if we're dividing things that have a common base, I can subtract the exponent. So that's exactly what I'm going to do. So I know that this first expression can be simplified, if you consider this being simpler, to 16 with an exponent of t minus 1. look at this. This has a base of 16. Since their bases match, their exponents would have to match to be equivalent. So this first one is not equivalent. All right, let's try the next one. Okay, these both have a base of 4. That means we can do the same rule with subtraction. We could turn this into a 4 with an exponent of 2t minus 0.5. Okay, so let's see. Is it possible to turn this into this easily? Well, we have a 2t, so there's a product, and we have some subtraction. I think it might be good if we tried to factor out this 2 and rewrite this as just a product. So if I factor out a 2, that would leave a t, and factoring out a 2 out of a 1/2, that's going to turn it into a 0.25. Okay, so now from here, I'm thinking we could use our rule that says that this is really 4 squared being raised to the t minus 0.25. That looks good so far because the exponent's matching, and now if I just continue this simplifying, we do see that the base is 16, and this one does match. So this one would be equivalent. All right, for our last one, right now we have a 16 as the base and a 2 as the base. So we can't do our division trick here where we're subtracting exponents. So we might want to do a little change of base. What if we took this 16 and we wrote it as a base of 2, right? We could do that because 16 is really a 2 raised to the 4th power. Don't forget that 16 already had a t on it, so this has a t on it as the exponent. Now we have a common base. I'm going to multiply these together. We get a 2 to the 4t divided by 2. And now because they have a common base, I care about that being a 1, we're going to do some subtraction. So we get 2 to the 4t minus 1. All right. Now, can we take this and turn it into this is the question. Well, if this 4 could be separated out, right, 2 to the 4th, we get the 16, that would work. So let's do it. Let's factor out a 4 from here. That would turn this into a 0.25 or a 1/4. I'm just going with a decimal since this one was a decimal. And there it is. Now we can use the 2 to the 4th to get us the 16, and our exponent matches the one above exactly. So this one was also equivalent. And again, this was just one way of getting through the simplifying process. I didn't touch the one at the top here. You definitely could have. But in the end, you have to be able to be flexible. It comes down to being flexible and understanding those rules to see if you can turn it into something else that matches. All right, good luck with your practice.